Our first presenter is going to be Ian Campbell. Ian is Ann Arbor, Michigan. You know, they don't plow the side streets when it snows there. I was there once in the winter. It was like very disconcerting. But Ian came into this program and got out of the snow and is here in lovely San Diego. And I'm really grateful that Ian's here, both because he actually got my music references from like the early 2000s that a lot of people don't get, and had pretty okay taste in kind of like punkish emo music that I was like, okay, it's not bad. And had seen some of the same random movies that I've seen, and then picked a topic that's just so close to my heart, because it's atmospheric rivers, which are a weather thing. I wasn't going to go on about what they are, but I'll let Ian do that, and how they impact vegetation and fire risk in California, which is an incredibly interesting topic. So our first presenter is an excellent student and really nice guy, and somebody who's going to be an extraordinary employee or colleague for his next supervisor. So there's a recommendation right there. Atmospheric rivers' influence on vegetation growth and wildfire risk across Southern California ecoregions. Ian Campbell, the floor is yours.
Thank you, Corey. Thanks everyone for coming in person or attending virtually instead of flying your private jet. I appreciate you being here. But before I begin, I would like to say a few words in solidarity with the students who, unlike our cohort, will not be graduating this weekend. At the beginning of May, a group comprised mostly of UCSD students set up a peaceful encampment on their own campus to protest the UC's financial ties to the genocide in Gaza. On May 6, a few days later, hundreds of police in riot gear showed up in the morning. The police violently arrested 64 of the activists, including 40 students. Subsequently, Chancellor Khosla sent out an email to the UCSD community in which he claimed, quote, "The decision to clear the campsite was made due to the consideration of the significant dangers to the people inside and outside of the encampment." He said this just after police had attacked my colleagues with pepper spray and beat them to the ground with batons. Now, 7 of these students are barred from graduating this weekend and still don't know whether they will receive their diplomas at all. I stand with their message, and I stand for many UCSD students when I say that we no longer have confidence in Chancellor Khosla to keep us safe. Thank you. And now I'm going to talk about some science. All right, so what are atmospheric rivers? So shorthand for atmospheric are ARs, and essentially they're long concentrated bands of moisture in the atmosphere. They're responsible for a huge amount of the moisture transport from the tropics upwards to the poles in both the northern and the southern hemisphere around the world. And each winter, they account for about half of the precipitation in California, but this can vary a lot. And this variability leads to California having the most variable precipitation of any state in the US. Orographic lifting, which is the process in which these atmospheric rivers move over mountains, leads to variable precipitation depending on the altitude. And they can vary on a scale from 1, which is generally seen as beneficial atmospheric rivers, to 5, which are generally seen as hazardous atmospheric rivers based on their length and their IVT transport, which is called integrated vapor transport, and I'll get into that later. This is the extent of my photo editing skills. So the average atmospheric river can carry 15 times the amount, a strong atmospheric river can carry 15 times the amount of water transported at the mouth of the Mississippi River. So they are a big deal in California. Now talking a little bit about wildfires. Half of the 20 largest recorded wildfires in California occurred from just 2018 to 2022. So this problem is rapidly intensifying, and it's extremely deadly. And in Southern California, the trend is a little bit more mixed. We don't see such a strong increase in fires. However, they are certainly growing more costly. In just December 2017, 29 fires broke out in Southern California. And between insurance raises and the cost of fighting the fires and property damage, it cost over $5 billion in just 1 month. So I wanted to answer a few questions linking atmospheric rivers to this trend in wildfire. So how do atmospheric-related precipitation influence vegetation growth and productivity? And how does this influence vary across different ecosystems in Southern California? And finally, what are the implications for fuel loading, which is the process of the increase in fuels available for wildfires to burn, and general wildfire risk in California? So here's some of my data. I took Level 4 ecoregions, which are essentially groups of vegetation communities from the EPA database. I measured vegetation greenness using the Enhanced Vegetation Index, otherwise known as the EVI. I looked at both winter precipitation and AR-associated IVT, which is the integrated vapor transport in the atmosphere, to measure the wetness of a winter. And I also looked a little bit at the Evaporative Demand Drought Index, also known as EDDI. So here's a map of the ecoregions. So you can see San Diego's down here, LA's up here. I generally excluded the more urbanized areas because of the introduction of non-native plants and palm trees and stuff like that that might mess with the data. And each color represents a different ecoregion. On the right, we have the vegetation key. So I sorted the primary types of vegetation in each ecoregion. And here's just a comparison of their mean annual climate to give you an idea of what these ecoregions look like. The redder the ecoregion, the hotter. The bluer, the cooler. So these are some of the mountains we have over here near San Diego. And these are the really high, hot and low, dry inland hills. And on the right, we have winter precipitation, which is somewhat representative of atmospheric river activity. And as you'd expect, the further north you go, the closer you get to the AR typical track. So generally, we see a bit more winter precipitation up here in contrast with some of the more dry ecoregions by San Diego. Now I'm going to talk a little bit about growing season productivity. So I measured growing season productivity by taking the maximum 5 EVI values for each ecoregion. And the lighter the value, the less growing we had, and the greener, the more we had. And on the right, we can see that the strongest correlation is in this ecoregion right here, which is the Diegan Western Granitic Foothills. And this is a very chaparral-dominant ecoregion. And a lot of the chaparral-dominant ecoregions, like their ecoregions up here, we do see that strong correlation. So that was the first thing I noticed. Now I took the August through October greenness, which somewhat represents the dry fuel going into the fire season. And you can see, again, the inland hills are very dry. We also see the Channel Islands are very dry. And both of these regions are dominated by grasslands. So this is telling us that by the fall, the grasslands have dried out and are basically ready to burn. Whereas if you look up here in the mountains, it's still very green in August to October. And again, we see a strong correlation between the winter precipitation and the fall greenness in those chaparral-dominant ecoregions. And now I took basically the difference for each year between the first graph and the second. And what you see is that there's a lot of change in greenness in this ecoregion up here. This is the Santa Monica Mountains and over here. And so this is telling us that each year where we see a lot of drying in these ecoregions and potentially a lot of fuel for wildfires. And the darker the ecoregion, the closer the correspondence between the winter precipitation and the subsequent drying. Here's just a look at the seasonal cycles across the different ecoregions. So what I did is I took data from 1984 to 2023 to show you how each ecoregion is changing in greenness from the winter to the next winter. And generally, these trend upwards in elevation, moving from grassland to chaparral to finally montane conifer forest. And so as we'd expect, earlier in the year in the grasslands, the growing seasons are favorable. And so we're seeing an earlier peak in the vegetation greenness, as opposed to the conifer forest, which is a much higher and later peak. Now, something I thought is interesting is if you look at this chaparral mixed forest ecoregion, we see a much longer peak in the EVI. And this actually informed my methods of measuring vegetation growth. So instead of taking just the one highest vegetation index, as many previous studies have done, I took the 5 highest. And that's because in a lot of these ecoregions, you get different plant communities peaking at different times, as seen here. So this graph, instead of just looking at precipitation, I wanted to connect this to atmospheric rivers. So I'm looking at the integrated vapor transport. So that's part of the measure of how strong an atmospheric river is. And these blue lines are the seasonal cycles of vegetation greenness after wet winters. And the red lines are after dry winters, or low atmospheric activity winters. And generally, again, these are moving upwards in elevation. So what do we see here? We can see in a lot of the lower elevation ecoregions, which have grasslands present, you get a really early peak in EVI, and you get a really early separation in vegetation greenness between the wet winters and the dry winters. Now, as you move to the more high elevation ecoregions, where it's more chaparral and forested, you don't really see too much of a difference in vegetation greenness early in the winter, but by the growing season, you do see a difference. And especially in the conifer forest, we see that this difference lasts until the fire season. So this is telling us that in general, the fuels are moister and more abundant in the conifer forest moving into the fire season. Here's another way of looking at those previous graphs, except this time I have all the ecoregions on the x-axis. This is their mean vegetation growth on the y-axis. And each ecoregion with stars means the results were statistically significant. So what do we notice? Generally, the kind of medium altitude ecoregions, which are chaparral dominant, you see a significant difference in growing season peak between the wet winters, or the high atmospheric river winters, and the dry winters. Another thing we can notice is that in a couple of the ecoregions, we see a lot of variability from year to year, even if it's a wet year and a dry year. And this is telling us that in these ecoregions, a wet winter is part of what corresponds to high vegetation productivity, but not the only factor. Temperature might also play an important role, as opposed to if you look at some of these more mountainous ecoregions, you see a lot less variability from year to year. And here's the same thing for the fall vegetation indices. So again, the stars are the significant ecoregions. And if I just go back, there's a lot of overlap. So now I wanted to tie this all to drought conditions. So October to August vegetation greenness in chaparral dominant ecoregions is more correlated with previous winter precipitation than with summer atmospheric conditions. What does that mean? So on the left, we have this graph of vegetation greenness and the 90-day eddy, which is essentially a purely physical drought indice that measures temperature, humidity, wind speed, and incoming solar radiation. So we see a bit of a correlation across some of the ecoregions between the fall greenness and the drought indice. But if you look at the graph on the right, the correlation is generally much stronger if you're looking at the correlation between winter precipitation and fall vegetation greenness, especially in these more chaparral dominant ecoregions. You see very little correlation here, not statistically significant, but a very significant correlation here. So that's telling us that chaparral is very sensitive to how much it's rained the winter before, but maybe less so to how hot and dry it is in the summer. To understand the implications of this for actual wildfires, we need to understand the difference between ignition-limited, climate-limited, and fuel-limited ecoregions. So here's a selection of 3 of my ecoregions. We have the Santa Ana Mountains, which are a mix of vegetation. We have the Southern California montane conifer forest, which is, of course, a conifer forest, high altitude, and then the hot, dry inland hills, which is largely a grassland. Grasslands are seen as fuel limited. In other words, the severity of the fire is generally limited by how much grass, how much fuel is available, and not so much what the climatic conditions are. But as we move to some of those more chaparral ecosystems, they're a little bit climate limited, but they're also just limited by the amount of ignitions they have. And so this is telling us that chaparral dominant ecosystems are really influenced by people moving into the wildland-urban interface and starting fires, where naturally there were only fires about 30 to 150 years. So tying that to the results I got earlier, we can see that winter precipitation has the strongest correlation with vegetation growth in chaparral. And knowing that chaparral is somewhat climate limited, we can assume that the implications for that are that winter precipitation will lead to lower wildfire risk come fall in chaparral, most likely. We also see this because the chaparral relationship grows more significant by the fall. We also know that winters with high air activity are likely, reduce risk in chaparral. Winters with have the strongest correlation with change in EVI in grassland and coastal sage dominant plant communities. Thus, winters with high atmospheric river activity probably increase wildfire risk in grassland and possibly coastal sage dominant ecoregions. And winter precipitation has a moderate impact on fall EVI and conifer forest dominant ecoregions with the potential for fuel loading over multiple years, which is something I'd like to investigate further. And also, winter precipitation is more correlated with these indices than just the atmospheric river EVI. So what are some of the implications for this? Save lives and money, proper land management like prescribed burns, forest thinning, and invasive species removal. And there's a potentially global application for ecosystems with atmospheric river dominant systems. And this leaves a lot of questions like, are there multiple year lags? How does winter precipitation impact the drought index? And would controlling temperature change my results, just to name a few? I want to give a big thank you to Kristen, who's here today, the rest of my committee, and I had so much help from other people. And I learned MATLAB this year, which was a huge challenge, and Kristen was extremely patient with me. So yeah, thank you to everybody for supporting me, my family for coming out, and my cohort for being just great people. So thanks, everybody. Any questions, comments, concerns?
Do you have thoughts about how some of this work or future work might help to provide decision support, for example, going into the fire season, say looking ahead from the end of winter?
Yeah, I think if we go back to the results, I think in chaparral dominant ecoregions, if you see a wet winter, there's probably going to be a lower wildfire risk come the fall season. So prioritizing prescribed burns is probably less of a priority after a wet winter in chaparral. Versus if you see a wet winter in a grassland ecoregion, you're probably going to be worried that there's going to be potential for a lot of fuel loading going into the fall. So you'd probably want to prioritize prescribed burns and vegetation thinning in the more low elevation grassland ecoregion communities. And yeah, I think moving into the conifer forest, I think generally what I've found is that conifer forest, it's more of a long-term trend with the potential for fuel loading as we've seen in Northern California after decades of fire suppression. So I think it really depends on the ecoregion. And I do think this approach, if it's explored further, could be applied. Yeah. Thanks.
I think they've got Hurricane Hunter type planes, 2 of them that went out this winter to help identify the streams. Do you know? How have their predictions been?
That's a great question. And Kristen is probably better suited to answer it than me. I'm not sure what the results have been this winter. Yeah, thank you though.
So Ian, you grew up in Michigan, I happen to know that, where precipitation is pretty even over the 12 months, and California is very uneven. And is that one of the reasons why wildfire is so dangerous here, that rain builds up fuel and then the rain goes away and it dries out? And I guess wondering, is that the future of California, if not worse, that you're going to get these cycles of huge buildup of fuels and then huge drying out?
I knew my dad would answer the question. Yeah, and I think especially a lot of predictions are that atmospheric rivers will grow both wider and possibly more severe going into the future. We've already seen that severe flooding in recent years, and that drought conditions could become more unpredictable and more severe. And yeah, it's likely that in the future we'll see more wet winters followed by more hot, dry summers with a high eddy. And yeah, this could lead to a lot of vegetation drying, a lot of fuel loading, and big wildfire risk across California. Yeah. Thank you.